produces rotation that is counterclockwise, then that torque is positive. If it's a torque that causes a clockwise rotation, it is negative. Okay, you have probably experienced torque in one way or another, but you haven't really thought about it, at least not in terms of torque or physics. Have you ever been bored, took a pencil and a CD, put a CD in the middle and then start spinning it? And throughout spinning it, the CD would either go up or would go down. That is the effect of torque. Because if the angle of rotation is this way or that way, your cross product would either be up or down. Let's take a look. Okay, let's do a sample problem. Nope, not this one. This one. Okay. We have three forces. Each one of them has a magnitude of 2 newtons. And they all act on one particle or on one object. We are given the positions of the particles, and we are given that the position vector is 3 meters and at 30 degrees from the origin. What is the torque about the origin due to each force? So this is the origin. This is where the rotation actually happens, but this is the point at which we are applying the force. We're applying 3 forces, F1, F2, F3. Each one is 2 newtons. And this distance is 3 meters. And this angle is 30 degrees. Well, let's do them one by one. Okay. F1 is in the in the plus x direction. It's 2 newtons. And the angle between it and the actual particle is 150 degrees. How do we know? Because we know this is 30, so the complementary angle to it is 150. 180 minus 30 is 150. Torque equals R cross F. Since this is one-dimensional, we can simply use RF sine theta. R is 3, F is 2 newtons, theta is 150 degrees, and we get 3 Newton meters. Okay. 3 Newton meters where? In which direction? Okay. In which direction is these 3 Newton meters? Well, if I cross R into F, okay, my R is in this direction, my F is in this direction, so my torque is inside the page, which is in the minus Y direction. Cross products always cause wrist problems. Okay, you need to start doing all sorts of weird wrist movements. Okay. Let's try another one. Let's look at F2. Well, F2 is down in the x-axis. Okay. So in the minus x-axis, so we have 30 degrees and another 90 degrees. That's 120. Plug the numbers in, 5.2 Newton meters. What about the direction? R, F, and it is outside. So in the plus Y direction. Now we have 3 Newton meters in the minus Y. We have 5.2 Newton meters in the plus Y direction. And finally, 3, which is the weirdest one because it goes in the plus y direction. Sorry, in the minus y direction. Okay. Again, the numbers are easy to put in. Direction, R. But now my F is actually inside. So it goes in it goes at a weird angle. Okay, it goes at this angle theta down. At 90 degrees to R. So these are my three torques. Okay, I end up having -3 here, plus 5.2 here. So this is 3 in the minus y direction, 5.2 in the plus y direction. And then I have 6, magnitude of 6 at 30 degrees, which means I have 6 cosine 30 in the x-axis and 6 sine 30 in the y-axis. Okay. Why y direction? Why which in y direction, Mariam? No, it's in the minus y direction, not y. So either I write it as 3 in minus y or -3 in y. Okay. Because it's not in the x direction, it's on the y-axis. This is the y-axis. Remember, our R and F were in the x and in the z. So our torques were, one was in plus y, one was in minus y. Cool. Let's take a simpler example. A planet in elliptical orbit about the sun is in the position shown, with the origin located at the sun. The vector torque on the planet is what? 0 along plus z, so out of the page, in the xy plane somewhere, or none of these? Okay, we have quite a few B's. Let's wait another minute and see what other people say. Okay, so a whole bunch of B's and a plus Z. Let's do the right-hand rule. R cross F. Where is R? R is in the XY plane, right? So this is R. If my planet, this is my planet, and this is my sun, R is in this direction, right? Okay. Where's my F? Where's my force? My force is no, what is the direction of my force? Okay, let me move into a whiteboard. Why is this not working? Okay, let's not confuse two things. All right, first thing first. A force cannot be clockwise or anti-clockwise. A torque can be clockwise or anti-clockwise, but a force cannot. Okay? A force is either in the plus x direction and the minus x, plus y, minus y, or a combination of those, or plus z, minus z, or a combination of those. A force is a direction. It doesn't have clockwise or anti-clockwise. Okay? That's the first thing. Second, okay, so that's the first thing. Second, let's look at this. This is R. Yes, this is the moment arm. Where is my force located in circular motion? If I am going through a circular motion, then we know torque equals R cross F, otherwise known as RF sine theta. My force is also going through this to the center, right? So what is the angle between my R and my F? And what is sine 0? Also 0. So my torque here is actually 0. Okay, and this is why our planets are in stable orbits around the sun. They don't end up going, all around the place up and down, because there's no torque. If there was torque on our planets, we wouldn't be able to go around the sun like this. We would be going in whole sorts of crazy orbits in 3D. Okay? So do not confuse between the clockwise, anti-clockwise of torques and between the directions of the forces. A force causes a torque. Okay, the torque can be clockwise, anti-clockwise, but not the force. Rayan, because it is a circular motion. And in circular motion, you have your centripetal force, which goes towards the center of the object. Okay. How perpendicular? Your R is towards the center, your F is towards the center, so your angle between them is 0. If the angle between them is 0, you cannot have a torque, because sine 0 is 0. If we say that the answer is B, points along the z-axis, then yes, perpendicular. Sorry, I did not notice that you were answering, Mariam. Okay. If this is the force at 90 degrees, we will have R, F, so it will be perpendicular that way. Or if this rotation is counterclockwise, then the torque would be up. Okay. But then we would all be dead because we wouldn't be in a stable orbit around the sun. Okay, a reminder of linear momentum that we did a couple of chapters ago. P equals mv. Now, as we have done over and over again, okay, every translational variable so far has had a we have translated it into angular variables. So we're going to do this. Angular momentum. In your book, it's not 11-3. It's not 11-5. It's 11-2. What is angular momentum? Let's look at two things, two objects. Okay. A whole bunch of things. Then we can do it. Now, if something is rotating about something else, it has a linear momentum, right? So if I have something here, this is my x point, and this thing is going counterclockwise, then at each second, at each point, it has a direction that is tangential, right? And it has a velocity of that tangential. So it has so it has translational momentum, okay, which is P equals mv. Yes, Adnan, there are no external forces in a solar system. Okay, if you take the entire solar system to be a system, then all the forces, gravity, blah, blah, are within the system to an approximation. Okay, so at each point, if we just take a look at one point and zoom in, this thing is going to be moving in this direction with P equals mv. But since this is P equals mv, it also has a moment r. Right? Hence, we again translate, okay, angular momentum, do all of this again. Okay, we'll have two components. We are going to end up with an angular momentum, which translates our translational momentum into angular momentum. What do you think that would look like, given all the translation rules we have? So we have done S equals R theta. We have done V equals R omega. We have done torque equals R cross F. What do you think our angular momentum is going to be? I omega RP. It cannot be RF because RF is already torque. Okay, so most of you are saying two things. They're saying that angular momentum is either I omega or RP. Okay, RP is the same as saying R mv. You're both correct. Okay, so angular momentum, we give it the letter L, or capital L if you want. Usually the small letter L is used. Okay, and it is, we have two components. Our velocity has a tangential component, V tangent, and we have V parallel to the center. So we have R perpendicular P, which is R sine theta P, and P we have already said is equal to MV. So we have RMV, so RP. We also have another component. If we take our P equals MV, we do the two components. Okay. We have P parallel and P perpendicular. Okay. Now, the only one of these that causes rotational motion is which one? Is P perpendicular, right? P parallel, the angle between it and the rotation is 180 degrees. Sine 180 is 0. Sorry, it's 0 degrees, not even 180 degrees. So, in terms of magnitude, we have L equals R cross P, which is the same as saying M R cross V. Now be very careful, there is a cross product here. And it says M R cross V, which is not the same as MV cross R. Okay, very, very, very important. These two are not the same. This is angular momentum. This is not. Remember, A cross B equals minus B cross A. So you'll have a sign problem if you try to put it there around. P is momentum, translational momentum, just MV. Okay, so what actually happens is you have R cross MV. Now, since M is simply a constant, we take the M out, and we end up with R cross. Okay. And in a bit, I'm going to tell you something that should hopefully tie all of everything we have done so far together. Okay. Direction, as usual, it's a cross product. So it is always going to be at a it's always going to be at 90 degrees to the two components, to the direction of to the R and to the translational motion. Okay. دائما لما نضرب تكون جي سالب لما نضرب ايش في ايش. We have our rule, remember? IJK, IJK, IJK. You go this way, it's positive. You go this way, is negative. Okay, so if you do I cross J, you'll get plus K. You do J cross K, you get plus I. But if you go the other way around, you go I cross K, you get minus J. K cross J, you get minus I, and so on and so forth. Okay. Let's do something. So we agreed that in a solar system or the planet, it has no torque. But what about angular momentum? How does the how does the magnitude of the angular momentum of the planet L with the origin at the sun at positions A and B compare? So if I calculate the angular momentum at B and I calculate the angular momentum at A, how will they compare? Will LA be equal to LB? Will LA be less than LB? Or will LA be more than LB? Can I activate these for you? No. I'm unable to activate these. Why not? Okay. Mind. I'm unable to get it to activate, Rian. That's what I was trying to do. But it's connected to Google Classroom, not to Moodle. Okay. But in your lecture slides, these are there. Okay. So how does the magnitude of the angular momentum compare? Well, let's see. L equals R cross P, right? R here is more, I'll use capital R, and R here is less. So we would imagine, okay, that L at point A will be more than L at point B since R is longer. Turns out though, that's not true. LA equals LB. And I'll explain why to you in a second. Okay. But first, let's take a look at this. Particles 1 and 2 move around point O in circles with radii 2 and 4 meters. So this is 2 meters and this is 4 meters. In part B, particles 3 and 4 travel along straight lines at 2 meters and 4 meters. And particle 5 moves directly away from O. They all have the same mass, and they all have the same mass and the same constant speed. We want to rank the particles along the according to the magnitude of their angular momentum. About point O, biggest to smallest. How would it be? Okay, we have answers all around the place. Okay. We have a bunch of B's, a couple of C's, a couple of D's, and then well, let's do it in order. 5 is in a straight line from O. So it cannot cause any rotation. Okay, the angle is 0. So sine 0 is 0, which means that the last answer need to be 5. It's the least, it's 0. So this cannot be right, and this cannot be right. These two can both be right. Okay. Now, since they all have the same mass, mv is the same for all of them. Okay. This will have 2p, and this will have 4p. So 1 equals 4p, 2 equals 2p. 3 would again equal to 4p, and 4 will again be equal to 2p, which means that L of 1 is equal to L of 3, and L of 2 is equal to L of 4. The greatest is 4p, so we start with 3, 1, since they're both 4p, 4, 2, they're both 2p, and then 5, which is 0. Okay. Okay, let's repeat. Let's write down what is L for each one of them. We said L equals R cross P, which is M R cross V. Okay. They all have the same mass, and they all have the same constant speed, right? Okay. Let's write it. What's L1, L2, L3, L4, and L5? What's L1? What's R for 1? For particle 1? 4. What's R for 4? And then whatever P is. Okay. Particle 2, R is 2. So 2 cross P. 3 is again 4 cross P. 4 is again 2 cross P. And here your angle is 0. Remember, this is a cross product. So you have sine theta, sine theta, sine theta, sine theta. 5, theta is 0 degrees. They're parallel. So 5 is simply 0. Now let's order these. You have 4p, 2p, 4p, 2p, 0. You want to go from biggest to smallest. So the order is 4p, 4p, 2p, 2p, and 0. The only one which satisfies this order is this 3, 1, 4, 2, 5. Explain, Ryan. So here we're only looking at the magnitudes. Okay, here we're only looking at the magnitudes. Okay, now here you have some angle, but in a minute this particle will come here. So it will have a different angle. Here you can imagine the same. You can imagine a circle. Right? So as they move, their angles will change. Okay, but their magnitude will remain the same. The reason 5 is 0 is because its angle is not going to change. It's not even going in a circle. It's just going away. So the angle is 0. Okay. Now, we've introduced torque. We've introduced angular momentum. Previously, we said we have something called the impulse, and we have also related the change in momentum, rate of change of momentum, to force. So we said dp over dt is equal to F net. Translate, dl over dt is equal to torque net. And since torque is a vector, you add it using vector addition. Yes, Rayan, you're correct. This is why you will see that I have left it as sine theta, sine theta, sine theta. I did not actually input anything for the angles. Okay, I did not input anything here for the angle. Okay. All right. Let's do a sample problem. Just like we did with, we looked at the change of momentum to find force, we'll look at the change of angular momentum to find torque. So we're looking at a freeze frame of a half-kilogram particle moving along a straight line with a position vector given by minus 2t squared minus t plus 5j. We want to find expressions for the angular momentum L and the torque acting on the particle, both around the origin. Okay. L equals R cross P, which is mR cross V. What is velocity? We have here position, right? We need to find velocity for here. Well, velocity is simply d by dt of position. Go back all the way to chapter 3. So I differentiate R. I do dr by dt to get v. D by dt of this will give me minus 4t minus 1 in the I direction. This is just a constant, so it goes to 0. I plug it in. R cross V. I will have R is minus 2t squared minus t in the I direction plus 5j. Let's do it. This is the revision of the things we did in chapter 2. Okay, so we have minus 2t squared minus 1, sorry, minus t. J is 5, k is 0. And V, we said, is minus 4t minus 1, 0, 0. Okay. Now, if you start doing the cross product as we did it in chapter 2, you will see that the only thing I have is in the I and in the J. So I will have minus 4t minus 1 times 5 plus, sorry, minus 2t squared minus t times 0, and I cross j is k. We end up with 20t plus 5k in the k direction meters squared per second. So L Because remember, we have mass is 0.5 kilogram. We multiply, we end up with this. Now, if I want to find torque, we know torque is dl by dt. So I just have to differentiate this. I will end up with 10 in the k direction Newton meters. Okay. Remember when in chapter 2 I told you, let's pay a lot of attention to this, and we're going to take quite a few lectures to master vectors. This is the reason, because they keep showing up again and again and again. Okay. If you go to do higher level courses in physics or in mathematics, vectors will just crop up at every nook and cranny. Okay. So for the cross product, you need to go back and revise how we did it in chapter 2. Okay. We said we will hide I first. Okay. So for the cross product, A cross B, okay, we said we will have AX BY minus BX AY in the I direction. And we have something similar in the J direction and something similar in the K direction. Now, the only thing we have here without all zeros taking over is I cross J. I will cross K away for the K component. I have these two. So I have minus T2 squared minus T times 0 minus five times minus 4T minus 1. This is equal to, this just goes to 0 because I'm multiplying by 0. This will give me minus 5 times minus 4 is 20T minus 5 times minus 1, 20T plus 5 in the K direction. Okay. Okay. So far, we have been looking at single bodies, single particles. What if we have a rigid body, an object, something like this? This is no longer a particle. It's a rigid body. It has empty stuff in it. So we cannot just simply do a static calculation. Yeah, we need to do the least favorite thing that we don't like. Now, if I look at this object and I look with it with a very fine microscope, and I take a very tiny piece of it with a tiny m, delta m, it's going to be going at mv in some direction with a tiny momentum, p equals mv. Now remember, v is different for each point in a circle, yeah, not omega v. So we need to do to take the rp or rmv of each tiny bit and add them all up. And whenever we say add them all up, we already know what's coming next, okay, the easiest thing to do is to integrate rather than to add up 2 billion different numbers. So we also know V equals R omega. So when we integrate, we want to reduce the number of variables to 1 or as close to 1 as possible. So we only do 1 integration or 2, not a whole bunch with different multivariate calculus. Okay, so since my R is changing and my V is changing for each and every bit, I'm going to do something. I'm going to change V into R omega. Why? Because once I put it back in here like this, okay, V equals R omega, I end up with omega, which is constant for anywhere on a rigid body, delta M, which is again a constant, but Ri changes. But then, do you remember what this is? Excellent, someone already wrote it down. MI Ri squared is your moment of inertia. So my L, my total angular momentum for this thing, is the sum of all the tiny Li's, which I can actually write it down as I omega. So in the previous few slides away, when some of you said it is R cross P, and some of you said it is I omega, you were both right. You were both equally right. We can either use I omega or R cross P. Okay. For rigid body, fixed axis, L equals I omega. Now remember when we did conservation of translational momentum? We said if two objects hit each other, there are different options, but momentum is always conserved. Turns out that is still true when you're going to angular, not translational momentum. Okay, so angular momentum is also always conserved. And if you have zero torque, okay, just like if we had zero force there, sorry, zero net force, okay, let's start over. I'll come back to zero again. My torque is dl over dt. What happens, okay, if I don't have any forces or any external forces? Everything is internal. dl by dt is equal to 0, which means the only way I can have a differential of 0 is if final equals initial. Okay, so we end up with a law of conservation of angular momentum, where we say the net angular momentum before is equal to net angular momentum after. Li equals Lf. If the net external torque on a system is 0, everything is internal, then the angular momentum remains constant. So this is the easy way of writing it down. If T net is equal to 0, Li equals Lf, I omega before equals I omega after. And if you remember a few slides ago when we spoke about the planet going in circles round and round, okay, yes. So when we had this, and we said point B and point A, yes, R here is bigger than R here, but then I also changes as you move away. Okay, so your angular momentum is actually conserved at all points. Your L is equal everywhere. Let's take a look at something. A solid sphere of radius r rotates about an axis that is tangential to a sphere with an angular speed omega under the action of internal forces. The radius of the sphere increases to 2r What is the final angular speed of the sphere? Omega over 4, omega over 2, omega, 2 omega, 4 omega. Okay. How about this? What on earth just happened? Well, since it is only internal forces, we know that Li equals Lf, correct? This means that I omega before equals I omega after. But what changes here, since the radius of the sphere increases to 2r, the I also increases. What is I for a sphere? I sphere before equals 2 over 5 mr squared, right? I sphere after is still 2 over 5 m, but now I have 2r squared, which is 2 over 5 m 4r squared, which is 8 over 5 mr squared. So I before is 2 over 5 mr squared omega before divided by 8 over 5 mr squared will give me my omega after. Yes, Dina, because it is a sphere. Moment of inertia of a sphere is 2 over 5 mr squared. Over 5 away, 2 and 8 simplify to 1 over 4. We end mr squared goes away. So we get omega A equals omega before divided by 4. Okay. Yes, Mariam? No, sorry, it's not half mr squared, it's 2/5 mr squared. So if we go to calculating moments of inertia, for a sphere, it is 2 over 5 mr squared. So Ayham, according to the question, the radius increases under internal forces. Okay, maybe the internal pressure of the gases, for example, increased. Okay. Because I want to know what is the final angular speed. So I want to have omega after omega final as the subject. I could have easily done it the other way around, or just now I can do it, and I can say omega I equals 4 omega final. It's the same thing. Okay. Now there's some cool stuff that can be done because of this, and I'll give you an example. We have a guy who's in a gym. Okay, 2 dumbbells. Now this guy starts rotating because it's really fun to start rotating around your chair. And when the 2 dumbbells are held out, he's rotating at some omega, at some angular velocity. Now what happens is he doesn't do anything. He doesn't move his legs. He doesn't do absolutely anything at all. Okay. He just moves it in. Okay. So the guy was rotating like this, and then he just did this. He brought them in, and suddenly the speed of the rotation increases greatly. Okay. It increases greatly. All right. Why? What happens is when he brings it inside, ماشي مكان ضيق ما يدور. Okay, but okay, I am able to go in a circle, but I don't have heavy dumbbells with me. Okay, you need at least some considerable mass. Okay, what happens is when he brings it inside, the inertia increases. Okay, the inertia increases, the moment of inertia I increases or decreases. Okay, I don't know exactly what the calculation is. If we assume he is a cylinder, okay, then it's going to be half mr squared. So when he is out there, it's going to be half let's see, half it's going to be half m 2r squared omega initial, and then he brings his hands in, so half m r squared omega final. So my omega final is going to be half m 4r squared omega I divided by half m r squared. The m's go away, the halves go away. So my final angular velocity is going to be 4 times as much as my initial one. Okay, moment of inertia has decreased when I brought it in. It's the same thing here. If you're into competitive sports, you will know that people who do swimming end up jumping, going in loops, 2, 3, 4 loops, and then going into the water. Okay, the reason they are able to do that is conservation of angular momentum. Something that we have actually heard many a time. Okay, the reason cats don't die when they fall out of really long heights, okay, is because cats, subhanAllah, have adapted to conserve their angular momentum. And what they do is they fall on their back, but in the way they conserve their angular momentum, they go in a circle. Okay. And what they do is before they get down, they actually end up spreading out or putting their legs in. And that changes their inertia, and that changes their force, and that changes the velocity at which they hit the earth. Okay. You know this. Okay. Let's see. Do you let it go or do you actually throw it? The increased force caused by throwing, okay, changes the physics. Okay. Remember, the amount of time the cat has before it actually hits the ground is very, very short. Okay. So if it's just falling from rest, if it's falling from rest, okay, then you're starting from v initial equals 0, and you're only undergoing acceleration according to free fall. Okay. The other reason is, okay, there's also the limbic system, the biological reaction. Okay. If a cat, for example, jumps, its limbic system is ready to fight back or to do whatever it needs to be doing. If you throw it away, its limbic system might not be ready. You can compare it to, for example, a friendly fight between two boxers. Okay, so when one boxer tries to land a punch, the other one is ready. Now, these same two people, if they were having a real fight, okay, on the road, and if someone suddenly punches him without him being ready, that person would probably fall down because its limbic system has not sort of activated the fight or flight reaction. Okay, so physics can only do so far, especially with living things. You have a whole bunch of biology. So a child stands on the edge of a merry-go-round. And if you haven't played one of these when you were a child, I'm sorry, you have lost your childhood. Go to a playground today and play it. Okay, which spins without friction. So this is a high-end model. The one we had at the garden by my home had bucket loads of friction. The child slowly walks towards the center of the platform. As the child moves towards the center, the platform's rotation rate, what happens? Does it increase? Does it decrease? Does it remain the same? Okay, we have one decrease. Okay, we have a couple of decreases and a couple of increases. The correct answer is it increases. There are no external torques. The child is already part of the system. Okay, so it's all internal. So angular momentum needs to be conserved. Now, what happens is when the moment of inertia becomes smaller, just like when we did the example now with the dumbbells or with the skater or with the other one. Okay, so what happens is your radius decreases, your I decreases, so your omega needs to increase to compensate. So another sample. A whole bunch of laws translated for you. if decrease بيكون طايح بيكون طلع من هذا. Yes, Azan, man, in the gym also the angular velocity increased. Okay, so this, to those who are asking, this is section 11.3, conservation of angular momentum. And your book has a few good examples. 11.4, precession of a gyroscope is not covered. Okay. So precession of a gyroscope is not covered. It's only 11.1 to 11.3 if you're looking at the OpenStax book. If you're looking at the other book I uploaded, it's 11.1 to 11.8. 11.9 is not covered. Okay. Okay. So Azan, both of them increase. In both cases, okay, yes, in both cases, the gym and the other guy, both of them increase. Look. The gym, final WF equals 4 times WI. Okay, and here as well, it increases. We did not calculate it, but we said it increases. The one that decreased was the solid sphere that became bigger. So I there increased instead of decreased. Okay. All right. Now, what I'm going to do is I'm going to stop the recording because YouTube is a real pain when I show you something off YouTube and record it.